Okay, welcome to my CCNA study guide. In this one, we're looking at Chapter 2, which is Ethernet Networking and Data Encapsulation. In this chapter, we're looking at the operation of a data network, understanding the purposes of the different types of devices, and we're going to get into some LAN switching technologies, collision domains and broadcast domains and such. So, legacy collision domain, we had hubs. So we actually had just one giant collision domain, but what is a collision domain? A collision domain is when we have more than one device trying to talk at the same time, and you'll end up with both devices headbutting one another. In reality, we got away from hubs and we got to switches. In a switched environment, every port on a switch that connects to a device is its own collision domain. And actually, this diagram is missing something. That is also a collision domain. Even between the ports on the switches, still a collision domain. A broadcast domain is separated by a layer 3 device. So if we're on a LAN and a node broadcasts, it should go to every device on that LAN that is not separated by a layer 3 device. It doesn't have to be a router. It could be a layer 3 switch or a layer 3 port or a routed port. So in this question, how many broadcast domains do you see and how many collision domains do we see? Well, we already know we have 2 broadcast domains because we only have a one layer 3 device, which is just a router. But how many collision domains do we see? Well, I see 1, 2, 3, 4, 5, 6, 7, 8, 9. I see 10 collision domains and 2 broadcast domains. This is important because I've noticed on certain CCNA exams, they'll ask you a question like, given the following network diagram, how many broadcast domains do you see? How many collision domains do you see? 2 broadcast, 10 collision, 2 broadcast, 8 collision, so forth. So, what mechanism do we put in place to prevent collisions? Whether it be a hub environment, whether it be a switch environment. We actually had this carrier sensing multiple access collision detection, CCNA CD. Into this, it's basically a rule that says wait random time if you detect a collision. Meaning, if I'm talking and you're talking, we both shut up. If we hear one another, we wait X amount of time, and then we try talking again. That's what CCNA CD does. So that's what CCNA CD does. Wireless works off something similar, except collision avoidance instead of collision detection. But we'll talk about that in a later video. So we also have half-duplex. Half-duplex is like a one-way street. You go one way. Meaning, we cannot send and receive simultaneously. We can only send or receive. So if one person is trying to send, while the hub is trying to send something, collision occurs. Full duplex, if we're working with a switch, it allows for sending and receiving. But on the hub environment, again, normally hubs, you're going to end up with more collisions because a hub is a multi-port repeater. So anything that is received on one port will actually go out all other ports. So hubs are in a way half duplex. So let's talk about a MAC address. What is a MAC address? A MAC address is a 48-bit physical address that allows us to have a layer 2 address. And normally it's broken up into two 24-bit sections. The first 24 bits is the OUI, or the Organizational Unique Identifier, which is normally assigned by IEEE, while the last 24-bit is vendor assigned, meaning if you get the first 24 bits of a bunch of 3COM cards, the first 6 numbers should be identical. Each one of these numbers is a hexadecimal number, so that's why there's 6 of them, each one of them being 4 bits. 6 times 4 is 24 bits. So if we're looking at just an Ethernet frame, so this is the frame part. It takes a packet and it puts header information on it to make it a frame, but it actually encapsulates a layer 3 packet. It will include things like destination, source, type, error checking, a preamble, and a few other things for error correction. Because we're talking about some basic material, we also have to talk about Cat5e and some UTP. There are 3 types of cables: a straight through, a crossover, and rollover. So a straight through is used between most devices. A crossover is used for common devices. So a crossover, switch to switch, router to router, PC to PC, PC to router. Those are all common devices or like devices. What about a PC to a switch to a router or to another PC? Here we can use just a straight through because we're connecting to a switch. But if we're hardwiring just one device to another, we have to use the appropriate cable. Granted, there's other technologies out there, MDXI, I always flip those. We're not getting into that just yet, because there are some auto-sensing technologies out there that are not standard yet. They're there, but there's no guarantee that it's always going to work on all switches. So the best course of action when you do this, you use a crossover for like devices, period. What is the pinout for a straight through? Normally we map 1, 2, 3, and 6 on both sides. For a crossover, we actually map 1 and 2 to 3 and 6, and we map 3 and 6 to 1 and 2. So let's look at this in terms of color. So if we are doing a crossover, essentially it's 568A on one side, 568B on the other. You're going to notice that 1, 2, 3, and 6, 1 and 2 will actually map to 3 and 6 on this side, and 3 and 6 will map to 1 and 2 on this side. That's what it means by a crossover. We switch these pair. People don't normally notice that color pattern shift in the IATIA 568A and 568B standard. So I wanted to point that out. Alright, so again, typical use for a crossover. Like devices. Straight through. Not like devices. So what about UTP Gigabit over crossover? This is kind of weird because it maps 1 and 2 to 3 and 6, but it also maps 4 and 5 to 7 and 8. This I have not found a straight standard yet, so have to be careful with this one. A rollover actually rolls over so that 1 on one side is 8 on the other, 2 is 7, 3 is 6, so forth. But normally, this is just a dedicated crossover cable. So on one side, it's a serial or RS-232, and on the other, it's an RJ45. So once we plug it in, what happens then? We normally will set some type of quick connect flow control for our serial. Normally we're looking at 9600 baud rate, 8 bits, no parity, and 1 stop bit. So if we're using like a SSH, if we're using like PuTTY or Terra Terminal or Hyperterminal, we'll be setting our serial connection ports or our serial connection settings for our specific port to those settings. And the other end, we're going to be connecting to our console. Normally you're going to see it a light blue cable because a console cable is a light blue cable. So UTP cable question number 1, what would we use between both of these two switches? Because they're two switches, we'd be using a crossover. Number 2, what would we be using between a console and a router? Yes, it is a PC, but notice what type of connection are we going for? We're looking for a console cable, and it'll normally be light blue. If it's dotted lines like that, it normally means crossover. So between these switches, they should not be solid lines. They should be dashed lines. So let's go ahead and move down to our data encapsulation. So we're almost done with this chapter, but we have to understand, what do we call the envelopes or the packages at each layer? Normally, layers 5, 6, and 7, we call just data. So if we take any of these items or the data at these upper layers and we package them down one, for example, we take all of this and we put it into a segment, all we end up doing is we take the data, we tack in a TCP header or a UDP header, we tack on the appropriate header, this becomes the segment. And so what we end up doing, if we go down to make it a packet, we actually then, that becomes this data here. We put an IP header on it, it becomes, this entire thing becomes a packet. And again, if we take the entire packet and we put it down here, and we add a frame, a header, and trailer on it, that becomes a frame. And then lastly, we have bits. So each one of these layers, the data portion normally is the entire PDU of the layer above it. So read through the exam essential sections together, look through the question in the back of the book, and that's actually it for this chapter.